Today, I want to go over the mass on the spring problem. This is going to be on your midterm, by the way, this exact problem with different numbers. So this is a fantastic application of DEs. This makes a good project one. Your group right now should be talking about what you want to do for project one and setting up a meeting with me. A couple of groups already tried to set up a meeting, and then Ian happened and we had to cancel those meetings. Just send me an email, we'll reschedule. Decide with your group what you want to do for your project, set up a meeting with me when everybody can be there, even if it's after hours. I'll work around your schedule. Let's decide what you're going to do for your project. Damped, undamped, and forced oscillations makes a great project. So taking what we're doing here today and going a little further with it. It's a really good project. Okay, so, excuse me, the basis of this is you got a mass on a spring. So like here's a picture, but I'm going to redraw all that. You guys have all taken physics, you know, simple harmonic motion, you know, mass on a spring, Hooke's law. This is our equilibrium position here, where the mass will just sit there. The spring's not compressed or stretched. We call that x equals 0. Then if we perturb that mass, if say we stretch it out, so here was x equals 0, and I move it out to some x equals x, then Hooke's law says there'll be a force that tries to push backwards. The spring's been stretched out, it tries to go back to normal. And that force will be negative kx. So this is the positive direction to the right. That force is going to be negative because it's pointing to the left. If I were to compress the spring, if I had the mass right here and I had some negative x value, then the force would be to the right because I've compressed the spring. The opposite of a negative is positive. Okay, so my only force here, if I draw a free body diagram, I'd have the weight pushing down, the normal force pushing up, and the spring, let's look at this one, this version, F from the spring pushing back. The sum of the forces in the y direction is 0. The mass is not bouncing up and down. So that just tells me my normal vector in magnitude equals my weight. We just ignore those. What about the sum of the forces in the x direction? Well, that would just be F, that spring force there. And that's negative kx. But I've taken physics. I know the sum of the forces is mass times acceleration. So that says ma, the vector a, is negative k x and vector x. Now these are one-dimensional vectors. We handle one-dimensional vectors by just using positives and negatives. So I could ignore my little vector symbols here and just realize positive is to the right, backwards is to the left, is negative. But wait a minute, we've taken physics, we know acceleration is the second derivative of position with respect to time, which a lot of times we'll call x double dot. So I get this differential equation where dot means derivative with respect to time. I'm going to make all that smaller. Run out of space there. I'll upload this document. That's a second order linear homogeneous with constant coefficients, dE. I'm going to move up here. I could rewrite that as mx double dot minus kx equals 0. Second order linear homogeneous with constant coefficients. And it's homogeneous because this side equals 0. We can solve that in our heads. So we assume x of t, x here is my dependent variable, is some e to the lambda t. Plug everybody in, we're going to get m lambda squared e to the lambda t minus k e to the lambda t equals 0. Factor out the e to the lambda t. We get m lambda squared minus k. Wait, something's not right. That's a plus. This was negative on the right. When I moved it over, that's plus. Sorry, plus equals 0. So my characteristic polynomial, m lambda squared plus k equals 0. So solving for lambda, we'll get lambda squared is negative k over m. Lambda is plus or minus I times the square root of k over m. So we get complex solutions. And maybe we'll write this, maybe we'll be more explicit here and say that's 0 plus or minus I square root of k over m. So remember, when you get complex solutions, the real part, whatever's here, goes in your exponentials, goes in your e's. The imaginary part, without the I, right here, goes in your sines and cosines. So we're going to name that number there omega square root of k over m. And then our solutions, our general solution, will be x of t equals e to the 0 is just 1. So it should look like a e to the 0t cosine this number t plus b sine blah, blah, blah. The e to the 0 is just 1, so I'm not going to bother writing the e part. And we've named this thing there omega. So this will be cosine omega t plus b sine omega t. Now, it's pretty easy to see that x of 0, my initial position of this mass, how far I've stretched it out. Well, sine of 0 was 0. Cosine of 0 was 1, will just be a. And it's pretty easy to see that x prime of 0, derivative of cosine is negative sine, sine of 0 is 0. Derivative of sine is cosine. Cosine of 0 is 1. We'll just get b. So that's my initial position there. That's my initial velocity. So let's take, for example, make all this small here. Let's say, for example, we had, I don't know, K is 20 newtons per meter and M is 5 kilograms. Then my initial DE would have been 5x double prime or double dot plus 20 x equals 0. I could just divide everybody by 5 here if I wanted to, or I could leave it like this. my characteristic polynomial is 5 lambda squared plus 20 equals 0. That's lambda squared is -4, which implies lambda is plus or minus 2i. So omega here, which is square root of k over m, will be square, like we're going to get the same thing here, square root of 20 over 5, square root of 4, 2. See, there's omega right there. So, and let's do this as a an IVP. Let's assume x of 0 is 3 centimeters. And let's say we're starting this mass on a spring with no velocity. So I've stretched out a spring 3 centimeters, let it go from rest. I need a little more space. I never give myself enough space. That ain't going to work. I think that'll be okay. Then my solution is just going to be x of t. I got to convert that 3 centimeters to meters. So 0.3 cosine of 2t. So omega here is my angular velocity. Think back to your trig class. When you took trig, the period, you even learned this in physics, of a trig function is 2 pi over omega, that number right there. So 2 pi over 2 will just be pi. So this guy is going to have a period of pi, and it's going to go like a cosine. So there's pi seconds. There's another period, 2 pi seconds. And it starts at 3 centimeters, 0.3 meters, and goes down to -0.3 meters. So this mass on a spring, if I go back to my original picture here, if I started out here at 3 centimeters, it's going to bounce back and forth forever. Okay, what if we make this more interesting? What if we add in friction or some kind of damping force? So we've got our mass on the spring here. We still got, say if this is x equals 0 here, we're out at x equals x. We've still got Hooke's law. Which is -kx. But now we're going to add in friction. And let's assume that we have some damping force. It doesn't have to be friction, but most damping forces act a lot like friction. So let's just assume friction. Let's call this B as a vector. That's some negative beta times our velocity vector. So friction in this assumption is going to point in the opposite direction from which you're moving. So if you're moving to the left, friction is going to be a positive and point to the right, because that's what friction does. It tries to change your velocity. It tries to slow you down, change your speed. So friction points in the opposite direction of the velocity vector. But velocity, we know that's just the first derivative with respect to time of position. So then some of the forces in the x direction, all the forces in the y direction cancel out, will be the spring force as a vector plus this frictional force as a vector. That will be negative kx minus beta x prime. But we know, we've taken physics, the sum of the forces is the mass times the acceleration. And we've taken physics, we know acceleration is the second derivative. So if we move everything to one side, we get this second order linear homogeneous dE with constant coefficients. And it's pretty easy to see here that our characteristic polynomial will be m lambda squared plus beta lambda plus k equals 0. Now, this can have more than one kind of solution, right? It's a quadratic. Quadratics can have two real solutions, one repeated solution, or two complex imaginary solutions. So let's just solve this in general. Let's use quadratic formula. Lambda will be opposite of b, negative beta, plus or minus square root of b squared minus 4ac all over 2a. Like, there's our general solution. I shouldn't say it like that. There's our general solution for lambda from our characteristic polynomial. Now, if the discriminant is positive, we get two real solutions. Let's call them R1 and R2. And then our solution will be x of t. If you get real solutions, you'll get some a e to the R1 t plus b e to the R2 t. Excuse me. And these are, at least one of these is always going to be negative, always. And in fact, the dominant one is going to be negative. And we get what's called an overdamped system. Overdamped meaning you get too much friction. So remember, here's our situation. I've got this spring that's trying to make this guy oscillate back and forth, but I've added in friction that's trying to slow this thing down. If I've got too much friction, the thing's just going to kind of slowly go back to equilibrium. We call that overdamped. We don't get any oscillations. We get a graph. We start at some initial amount, some x of 0 here. And then either the graph just kind of goes like this over time. We get like an exponential decay. Or sometimes you might get like one oscillation. Here's x of 0. Maybe it'll go past equilibrium and then come back from the other side. So the mass started here, it got past equilibrium, and now it's compressing the spring. So the spring's trying to push it back, and it just kind of slowly goes back, but it doesn't bounce back and forth a bunch of times. We call that overdamped. And that happens when the discriminant is positive. What if the discriminant is negative? So what if that thing is negative? Well, then we get complex solutions. We'll get solutions a plus or minus bi. Then my general solution will be a e to the at cosine of bt. That's a little b. It's not beta. Plus b, which looks a lot like this beta. Different. Maybe I should use c here. Maybe I'll call this c. E to the at sine of bt. So we get the same kind of oscillation we were getting, but now it's damped. We call this underdamped. So we'll get a graph that still oscillates back and forth, but those oscillations are getting smaller and smaller. The amplitudes are getting smaller. The period is constant. So this time here is the same as this time here. So still take, this is really cool. This is why pendulums work, by the way. Pendulums follow a very similar kind of model. This is why you can have a pendulum clock. So even though the pendulum may not swing as far each time, it still takes the same amount of time to go through an entire swing. This is how pendulum clocks work. How quartz watches work too. It's a little different, but a quartz watch, electricity makes quartz vibrate at a certain frequency, has a certain period, and even when your battery is going bad, it might not vibrate as high, the amplitudes might go down, but a particular piece of quartz is always going to vibrate at the same frequency. And they use that to tune your watch. So this would be some x of 0 here. This would be time. This would be x. Okay, there's one other possibility. What if that discriminant actually equals 0? It's a beta. Then we call this critically damped. Because it's right at the boundary between this and that. So we remember from college algebra, if your discriminant equals 0, you get a repeated solution. Like we can just see what we would get here. If that equals 0, then that all disappears. Lambda is negative beta over 2m repeated. I spelled repeated wrong. Sorry. Repeated. So then our solution, x of t, we know what to do with a repeated solution. We'll get a e to that thing. Let's call that r, e to the rt. Plus then we pick up on our second solution. Oh yeah, I said I was going to call this c. On our second solution, we pick up an extra t because we have a repeated root. And this solution is going to look exactly like overdamped. Critically damped is just the very first overdamped. Okay, let's make up some numbers, and literally I'm just going to make up numbers here. I don't know which one of these we're going to get. I am kind of shooting for one, but let's see. So let's assume, I don't know, maybe K equals 20 newtons per meter. M is 2 kilograms. And our friction, our coefficient of friction is 3. I got to think about my units here. These coefficient of frictions have weird units. I always have to think about it. When I multiply it by a velocity, I should get newtons. So it's really newtons divided by velocity. So that's newtons over meters per second, not squared. So which I guess would be Newton seconds per meter. Doesn't matter. Okay, let's plug everything in. I mean, I kind of have the solution up there. I could just plug in there, or I could just work this from the beginning. So we're going to have two x double dot equals negative 20x minus 3x dot. This is MA equals negative kx minus beta b. A is the second derivative, B is the first derivative. So we move everybody to one side, 2x double dot plus 3x dot plus 20x equals 0. I get my characteristic polynomial, 2 lambda squared plus 3 lambda plus 20 equals 0. Maybe it factors, maybe not. I'm just going to use quadratic formula. Lambda is opposite of b, plus or minus square root of b squared minus 4 times a times c all over twice a. So negative 3 plus or minus, let's see what we got there. That'd be 8 times 20, so negative 160 plus 9, I think, is negative 151. Okay, so we got complex solutions. That means we're underdamped. Complex solutions are underdamped. So lambda is negative 3/4 plus or minus I times square root of 151 over 4. That's my A in my complex number. That's my B. Don't use the I. Then my solution is x of t is some A e to the negative 3/4 t cosine of root 151 over 4 t. Don't forget your t plus whatever b e to the negative 3/4 t sine root 151 over 4 t. T is not under the radical there. I want to kind of really emphasize that. T is not under the radical. Okay, I know what the solution is going to look like. I can draw this out. Let's say, for example, let's assume here x of 0 is 7 meters. Well, this is something huge. This is a big spring, I guess. X prime of 0 is 0 meters per second. It's still the same case that A, the number in front of the cosine, is my initial amount. The number in front of the sine is my initial velocity. So my particular solution is going to be 7 e to the negative 3/4 t cosine root 151 over 4 t. I'm going to get something that goes like a cosine, but decays, so it gets smaller and smaller. What about my period? My period t is 2 pi over omega, 2 pi over the number inside there. So 2 pi over root 151 over 4, whatever that is. I'm just going to call that t for now. So we started at 7. Here's one period, and I'm not going to go quite as high by the time I reach the end of that period, but now I'm at 1 period. And then for the next period, I'm not going to go as high again, but it's still going to take the same amount of time to go through a complete cycle. There's 2 periods and so forth. So here's time, here's position. That's what a graph would look like. Okay, so that's damped, underdamped, overdamped, and so forth. We can also have forced oscillations. So maybe you get this mass on a spring there and an earthquake happens and the ground is shaking. Or maybe you've got some kind of motor on that mass that's making it go back and forth. So we could have everything we just had. So you've got, like, if this is x equals 0 here, you got some spring force pointing backwards. You've got some frictional force pointing opposite of velocity. But we could also have some force function. Maybe we'll just call him capital F as opposed to F spring here. They could look like anything that's pushing this guy. Maybe it's constant. Maybe I've just got a guy over here that's pushing backwards on it. Or maybe this goes like a cosine or a sine. This could be anything. And then you get all kinds of crazy solutions. A classic example of this is the Tacoma Bridge massacre. I'm sure you guys have seen that video. I don't know if you'll be able to hear the sound.
And behind us is the Tacoma Narrow Strait Puget Bridge over the Sound.
To move
Look at that.
vertically,
Look at that.
up and
Look
down.
at that guy.
That's when the construction workers gave it the name Galloping Gertie.
The wind was oscillating at a particular frequency or causing oscillations at the resonant frequency of the bridge. And it was pumping energy into the bridge, which eventually caused the bridge to collapse. There are also examples of people marching across a bridge and they happen to march at the frequency that the bridge wants to oscillate at anyways. That's called the resonant frequency. The Millennium Bridge in London that just opened, what, at the Millennium, I think? I don't remember when it opened. But they opened it up and thousands of people walked out onto it. And it just so happened that the resonant frequency of the bridge just naturally happened to match up with like normal person walking speed. So because you had thousands of people walking on it, the whole thing started to vibrate and it started getting worse and worse and the whole thing started swaying. This is the reason that soldiers, when they're crossing a bridge, will break march, and they won't march across a bridge. They just walk normally, because there have been cases of soldiers marching across a bridge at a particular frequency that happens to match a resonant frequency of a bridge and making a bridge collapse. So this whole concept makes a great project idea where we throw in some nice, interesting forcing function and discuss all this. The rest of this, all this damped, undamped, underdamped, is going to be on the midterm. I'm telling you now, a problem a lot like the one we just did is going to be on the midterm. Make sure you know this material, or make sure you understand it at least. All right, that's a good place to stop.